Okay, this is question 19.38, and it basically just asks you to provide the reagents that you would use to make this alkene. This is a Z alkene. And yeah, how would we do this? Well, if we think about breaking the carbon-carbon bond and we think about retrosynthesis, we have two possibilities for an alkyl halide, right? We could either take this part of the molecule here, and then we could have our alkyl halide, let's just choose a bromide, okay, like this, or we could take this side of the molecule here, and then we could start with an alkyl halide, an alkyl halide like this. Son of a gun. It looks like this. Okay, well, if we compare these two, this is a secondary alkyl halide, and this one is a primary alkyl halide. And so this would be the best place to make our Wittig reagent from, would be from a primary alkyl halide, which we could use to make this Wittig reagent, okay, like this, okay, PPH3. So that's the Wittig reagent that we're going to use. And then the ketone is going to come from this part of the molecule. So we're going to take this Wittig reagent and we're going to take this ketone. Okay, well, I could draw it a little neater than that maybe. There we go. So that's called butanone. All right, so how would we put all this together? How would we do this? Well, we would start with the primary alkyl halide. So this is 1-bromopropane. So we'd start with our 1-bromopropane. In the first step, we're going to treat it with triphenylphosphine. So we'll treat it with triphenylphosphine. I'll draw out all the steps here. So step 1 is triphenylphosphine, put in a lone pair. So we're going to do an SN2 like that. That's going to give us the phosphonium salt. So we've got our 3 carbons now. We've got a phosphorus. Phosphorus is in group 5A. It's got 4 bonds, no lone pairs. It's going to have a +1 charge. You've also got the bromide. That's why it's called a salt. So what we're going to do is we're going to pull off one of the protons here using butyllithium. So let's write out, there's our butyl carbanion, there's our lithium. So we're going to rip off this proton in order to make our Wittig reagent. And I'm kind of running out of space here, but I'll do my best to draw it. So it's going to look like this. There we go, our positive charge here and our negative charge here. This is our Wittig reagent, okay? Then we're going to take our Wittig reagent and we're going to react it with our ketone. So we're going to take our ketone, right, like this, and we're going to treat it with our Wittig reagent like that, and that's going to give us our desired product. It's going to give us this guy. There you go. So that's the overall reaction. Now, if I had to write this out the simplest possible way, and there's probably a bunch of ways that you could write this reaction out, but I would say, probably the simplest thing to do would be to just write the structure of the ketone like that. And then I would just say, yeah, I would just leave it like this. I would just say the ketone plus the Wittig reagent. Okay, and you could draw the ylide or the ylene. Like if you want to write, if you want to show it with a double bond, there's no problem with that. You could just write it like this. And that's probably how they do it in the solutions manual. And there you have it. So that's going to be the most efficacious. Again, the question was, what's the best option? To start with a secondary alkyl halide or to start with a primary? And a primary is a better choice. And there you have it. So let's take a look at B. B, we're trying to make this trans compound here. So this is an E alkene like this. Now it's symmetrical, so we break the carbon-carbon double bond, and that tells us that we're going to have this, and if you chose iodide or an iodo instead of a bromo, that's no problem, okay? So we take this to make our Wittig reagent, right? So what's that going to look like? It means we're going to start with benzyl bromide, which is the name of this compound. Step 1, we treat it with triphenylphosphine. Step 2, we treat it with butyllithium, right? And that would give us what? That would give us this. Oops. 3PH3. That gives us our Wittig reagent. And then all we have to do is take our starting ketone, which is going to be this. We just have a double bond to oxygen. So we're going to have benzaldehyde, and you can write it out whatever way you want. You can write it like this, either way, benzaldehyde. And then you're just going to treat it with the triphenylphosphine derivative here, the Wittig reagent, and that's going to give you your product. And that is the Wittig reaction, my friends. And again, since this is a stabilized ylid, and if you're wondering, why is that a stabilized ylid, Mr. Dion? It's because if you draw it as an ylid, where you have the positive charge here and the negative charge here, and if we draw out the whole aromatic ring, right? So if I draw out the aromatic ring, I can show the delocalization of this lone pair, right? Well, maybe I should move the negative charge. So there we go. I have a lone pair here with a negative charge. So I can show the delocalization of that lone pair throughout the ring, right? And I'm not going to spend the time drawing every resonance contributor, but you could draw it like this, right? Son of a gun. Okay, and you could spend the time drawing out all the resonance contributors, but that's the bottom line. Okay, since this is, and I'll just write it down here, this is a stabilized Wittig reagent. Therefore, it's going to give you the E alkene. And we end up with the E product like that. There we go. So that's some good practice on Wittig chemistry. Again, we looked at an example where we had to choose the appropriate Wittig reagent, which came from the primary alkyl halide, which would, of course, this SN2 would go in a higher yield, using triphenylphosphine, anyhow. And then, of course, the next one was symmetrical, so there's only one possibility. But anyhow, that's how you do a Wittig reaction. Very cool reaction. All right, let's take a look at the last section. It deals with a new reaction. It's called the Baeyer-Villiger reaction. I'm going to show you that reaction right here. Baeyer-Villiger oxidation, another reaction that's a really old one, but a very important reaction in organic chemistry and still widely used to this day. So if you take an aldehyde or a ketone, right, that's the whole topic of chapter 19. It's all about aldehydes and ketones. If you take an aldehyde or a ketone and you treat it with a peroxy acid, like this is what we call a peroxy acid. Peroxy acid, okay, which has this Lewis structure, right? You've got the two oxygens here like that. Well, the peroxy acid is going to insert a carbon between the carbonyl and one of the neighboring alkyl groups, okay? So there we go. So you actually convert the aldehyde or ketone into a carboxylic acid or an ester. Here's the mechanism. It's a really cool mechanism because it only involves 3 steps. A nucleophilic attack by this oxygen. It attacks the electrophilic carbon. You do a proton transfer, and then this really cool rearrangement. You see this whole, there's 1, 2, 3, 4 curved arrows here. You end up losing a carboxylic acid. Anyhow, it's a very cool reaction. But the bottom line is that you insert an oxygen between the carbonyl carbon and an R group. Now the question becomes, what if my 2 R groups are different? What if it's R and R prime, for example? What do I do then? Well, we're going to talk about that in a second. But if you take a cyclic ketone and you try this reaction, right, this is symmetrical. So it doesn't matter which side we put the oxygen. We can put it here or here. We end up with the same thing. But when you have an ester that's cyclic, that's inside a cyclic compound, it's not called an ester anymore. It's called a lactone. And that's a new functional group that you need to be aware of. So what I was trying to get to before I forgot about the lactone was that, if you have an unsymmetrical ketone, or if you have an aldehyde, right? So let's say you have an aldehyde, which is this, okay? We have a hydrogen. And then if you have an unsymmetrical ketone where you've got 2 different R groups, well, which side is the oxygen going to be inserted on? If you have an aldehyde, the oxygen will 100% of the time go in between the carbonyl carbon and the hydrogen. So you'll always get a carboxylic acid if you have an aldehyde. After that, it goes tertiary, secondary, phenyl, and primary are next. So sorry, tertiary, secondary, and phenyl go together, then primary, and then methyl is last. So I would recommend memorizing this for your quiz. I probably won't ask you about migratory aptitude on your final exam, but you do need to know it for your next quiz, okay? And yeah, the easiest one to remember is if you have a hydrogen, you end up making a carboxylic acid 100% of the time. So hydrogen, tertiary, secondary, and phenyl are tied, primary, and then a methyl is last. Something that's funny about migratory aptitude is, and I don't even think our textbook goes into any detail about this at all, but this isn't all that well understood. Migratory aptitude is not highly understood, as is my understanding. So there's no way to really predict. You kind of just have to just kind of memorize it. Yeah. So even if you look up, you look at a really highly advanced organic chemistry textbook, they're still going to tell you that the factors that control the migratory aptitude are not completely understood. Anyhow, let's take a look at some examples. Again, I have the migratory aptitude written on here. So here we have an isopropyl group, right? So this carbon has 1, 2, so it's secondary. And then over here you have a methyl. Well, the migratory aptitude states that we're going to go with the secondary first, so the oxygen would insert right here, and it does to make this ester. If you have benzaldehyde, like here, well, hydrogen has the highest migratory aptitude, so you end up with benzoic acid. So just treatment with a peroxy acid. Now notice that it doesn't say MCPBA or anything like that. It just says a generic peroxy acid, and I think there's a variety of different peroxy acids that can be used. Well, with all that in mind, let's try a question. I think the only way to answer this question is to start by writing down the migratory aptitude, which goes hydrogen first, tertiary is second, secondary and phenyl are tied. So I wouldn't give you anything where you had to battle between those two. A primary and then a methyl is the lowest of the low. Okay, so if we look at the first molecule here, the first ketone, we have the carbonyl carbon. Then we have this carbon that is attached to 1, 2 carbon, so it's secondary. Then we have this carbon, which is attached to only 1 carbon. So we're going to go with the secondary versus the primary. So we're going to do the insertion right here. And so when we do that, what's it going to look like? Let's write it out here. We've got the carbonyl. We've still got this ethyl group. Now we've got now we've got an oxygen attached here, and then you have the whole cyclohexane ring. So come on, I'm trying to draw it neatly here. And there we go. So that's what you'd end up with. So this would be called cyclohexyl propanoate, and we'll look at ester nomenclature in the next class. The next one's an aldehyde. Aldehydes, again, are pretty simple. I don't like to use the word simple in organic chemistry, but if you have a hydrogen, whenever you have an aldehyde, you end up with a carboxylic acid. So let's draw the carboxylic acid that would be produced. It's going to look like this. Like that. We have our carbonyl. And there you go. So that would be called 2-ethyl butanoic acid, which again, we'll look at carboxylic acid nomenclature in chapter 20. Again, if you're wondering, how did you know? I used the migratory aptitude. Here we have a hydrogen, and on this side, this carbon is attached to 1, 2 carbon, so it's secondary. So hydrogen is going to win over a secondary, and then the secondary would win over a primary. And there you have it. Those are all the new reactions for chapter 19. If you take a look at synthesis strategies, I mean, there's so many questions that we can ask ourselves now at this point in organic chemistry too. Have we made a change to the carbon skeleton? Are we increasing the number of carbons? Are we decreasing the number of carbons? What about functional groups? In terms of changing the carbon skeleton and what we learned in chapter 19, you've either got to use a Grignard. So here's a Grignard reaction. You've got to make a cyanohydrin. So cyanohydrin. You've got to, not cyanohydrid, cyanohydrin. You've got to do a Wittig reaction, right, in order to change the carbon skeleton. And you can see that these carbons that are highlighted in red and the reagents are incorporated into the final compounds. What other kind of strategies can we think of? You know, you should be able to pretty quickly come up with a list of products and reagents, products that can be made from aldehydes or ketones. So you should be able to come up with all the different reagents for all of these different transformations. I'm not going to cover it right now because me just regurgitating the information in front of you doesn't help a lot. It really helps students when they sit down and they, make sure that they know what's going on in here. And remember, everything in here, these are all reactions that we would have covered before. Okay, so these are all pre-chapter 19 reactions. But then once we can make an aldehyde, well then, the sky's the limit, right? We can make so many different things from aldehydes based off of what we learned in chapter 19. we're going to come back to this question in a few minutes about some synthesis problems. However, I want to take a quick peek at the section on spectroscopy. We shouldn't just throw spectroscopy in the trash after organic chemistry 1. It should still, it still plays a pivotal role in organic chemistry 2. So, a couple of things that you should remember. I'd say right off, you should remember that if you have a conjugated carbonyl, that it's going to have a lower absorption. So it's going to absorb a lower frequency of electromagnetic radiation because the bond is weakened. And you should remember the relationship between wave number, right? So wave number is equal to 1 over 2 pi times the speed of light times the force constant divided by the reduced mass to the power of a half, like that. So if the bond strength decreases, right, then the wave number is going to drop too. Okay, so something to think about there. In terms of ring strain, increasing wave number, I've never asked a student about this before, but as the rings become more strained, the wave number of the absorption for the carbonyl gets higher and higher. You should know the aldehydic proton or carbon hydrogen stretch, which it says here it's 2700 to 2800. I think it's more like 2750 is what it says in our book, and 2850 reciprocal centimeters. So that's something to always look out for, right? Here's a aldehydic carbon hydrogen stretch. You draw a line with a ruler here. Come on, ruler, do your thing. Rich young ruler. Here we go. So if we draw a line here, so this is 3000. What is this? That's 2900. Now, what is it? 26, 27, 28. So yes, 28, 30, right? And then here we have 27, 19. So these are the aldehydic carbon hydrogen stretches. So we call that aldehydic CH stretching. And there's always 2 of them. That's kind of a dead giveaway for an aldehyde. What else do we have here? In the proton, you know that the methylene has a baseline of around 1.2, but if it's next to a carbonyl, what do? We add 1.0 ppm, and we end up with around 2.2 parts per million. You should know that the proton of an aldehyde is going to be highly deshielded, comes out around 10. And for a carbon-13, a carbonyl is going to produce a signal around 200 parts per million. And the signals usually aren't all that strong. They usually don't have a very strong signal. So this is the review of reactions. This might be worth, printing out and reviewing several times before your next quiz. Make sure that you know all the reactions in here, right? You want to make sure that you know about hydrate formation, right? Acetal formation, a cyclic acetal, a cyclic thioacetal. Rainy nickel can reduce it to an alkane. You want to know about imine formation, enamine formation, a hydroxylamine or an oxime that comes from hydroxylamine rather. You want to know about a hydrazone, which is a type of imine that comes from hydrazine. You want to know that you can reduce a carbonyl with lithium aluminum hydride or sodium borohydride. You want to know your Grignard chemistry, your cyanohydrin formation, your Wittig chemistry, and the Baeyer-Villiger reaction, which is the last one. So that's a lot. You know, what else? I'm missing one here. Oh yeah, the Wolfkishna, right? This one down here. Wolfkishna. I hope I'm spelling that right. Anyhow, which is the reduction of the hydrazone to an alkane. So there's a lot of new chemistry in here. It's a lot of great chemistry, really powerful chemistry, but there's a lot of new chemistry. And if you, and I'm not telling you this to try to intimidate you or anything like that. I don't believe in that kind of thing. But you know, if you just want to look ahead at chapter 20, what you're going to see is you're going to have a review of reactions that's going to be just like this or even bigger. So we learn a lot of new chemistry in chapters 19, 20, and 21. Tons of new, and chapter 18 too, didn't we? In electrophilic aromatic substitution, tons of new and exciting reactions. And so what's the best thing you could do? First, I would recommend making some flashcards maybe, or just sitting down and trying to memorize all the different reactions. Then you want to step into the practice problems in the back of the book, and you want to try as many of those as you can. Out of the ones that I suggested, if there's any that I left out, don't worry about those. You've already got enough on your plate just by tackling the ones that I did include. So you'll want to take a look at those. So yeah, where does that leave us? That leaves us with this last question, which was a synthesis question. And it asks you to propose efficient syntheses for all of these different transformations. So some really interesting transformations here. And I'm just looking at what I wrote down because I tried these earlier today. And you know, these aren't your run-of-the-mill, 2-3 step problems, are they? You know, these ones, especially the first two, take a few steps. I mean, what are the things you want to look at? I mean, here you're changing the carbon skeleton, you're adding a carbon, you're also adding a hydroxyl. So for the first one, cheapers, what happened there? Where did my problem go? I got a lot of problems. Come on. I just had this great thought and then the slides went away. You know, but just thinking about the first one, right? Just in terms of retrosynthesis, and that's kind of the way you got to solve these problems. If you had this compound, right? If you had 2-methylcyclohexanone, then all you'd have to do is treat that with a Grignard. So then the question becomes, well, how do I install a carbonyl here, right? How do I install a carbonyl there? Well, then I just think, well, if I had this alcohol, then I could just oxidize it. Well, then the question becomes, how do I put a hydroxyl here? Well, remember that when you're starting it with an alkane, you've really only got one option, right? And that would be to treat it with bromine and light, and that would put a bromine here. Make a better bond than that. That would put a bromine here. So if I installed a bromine there, then I could do an elimination to make a double bond here, right? And then I just do an anti-Markovnikov addition of water, oxidize it. Oops, I didn't mean to do that. Oxidize it, and then I do some Grignard chemistry, right? So that's kind of the approach that I would take with that one. So you can see how retrosynthesis comes in really handy for these. You notice this one, you're going from a cyclic structure to something that is acyclic. So you're breaking a bond. I mean, you don't have many ways to do that. You don't have a ton of different ways to do that. You also notice that you're changing the carbon skeleton. We're starting with 7 carbons and we're ending up with 1, 2, 3, 4, 5, 6, 7, 8, 9. So we add 2 more carbons, right? So something else to think about there. And in the last one, what I notice here is that I end up with a Schiff base or an imine. So I can, in terms of retrosynthesis, I must have, come on, what am I doing? Am I just erasing everything? I must have, where's my pen? I must have this carbonyl compound at some point. I've got cyclohexane carbaldehyde, and I would have to treat that with, the primary amine like that. So these are the kind of thoughts that we want to have before we start these types of problems. So what I want to do right now is take a short break, maybe 10 minutes or so, and I want you to try these problems before we go through all the answers. You got to give it a try yourself. Just watching me solve it, there's some learning can be done there for sure, but you want to be confident that you are able to answer the question on your own.